Good morning, everyone. Morning. Good night. Good evening. How are you? It's been a long day. My name is Isabel Kingsley, and I'm the manager of Sydney Science Festival, and I also manage the Partnerships and Festivals team here at the Museum of Applied Arts and Sciences. And I'd like to welcome you tonight to the talk, The World's Greatest Science Experiment, a talk by Dr. Alan Duffy. Just going to start off with some acknowledgements. So I'd like to acknowledge the land of the Gadigal people of the Eora Nation, whose land we meet on tonight, and pay my respects to elders past and present. So this talk is part of Sydney Science Festival. I'm so glad to see so many of you out here tonight to see this talk. Sydney Science Festival has a whopping over 100 events across the city, and it's a huge collaborative effort by 62 organizations throughout Sydney. There's all kinds of really great activities and events, from talks to workshops, exhibitions like Collider that you just saw. Who loved Collider? Yes, it's amazing. And talks like tonight. So let me introduce our special guest. Dr. Alan Duffy is an astrophysicist and cosmologist from Swinburne University in Melbourne. He creates universes using a big supercomputer to understand how galaxies form and to probe nature of the nature of dark matter. He's made over 100 appearances on radio and television and print. He's been very, very busy the last few days being the ambassador for Sydney Science Festival, so you might have seen him in the newspapers, on telly, on radio. Currently, he is at the Center for Astrophysics and Computing at Swinburne University, and he's co-investigator of the first dark matter detector in the Southern Hemisphere called SABRE, which is at the bottom of a gold mine. So we are very lucky to have Alan here tonight. So please put your hands together and welcome Dr. Alan Duffy.
Thank you. Thank you so much for the kind words and the nice introduction, Isabel, and thank you to the Sydney Science Festival team in general. I was there at the event last night, and I had the fun of getting to run around and just talk about some cool science, and then get to play with all the exhibits while all the staff had to work hard and get absolutely swamped by thousands of people. So that was a tremendous start, and it's a real privilege to be able to kick off the talks series through the Sydney Science Festival with a truly spectacular topic, which is, of course, the Large Hadron Collider. Now, I'm glad that I think actually almost every hand went up when Isabel asked, had you seen the Collider exhibit? So you're already experts. So that's wonderful. I would point out my background is astrophysics with cosmology, which means that I study the universe on the largest scales. I concern myself about what's in that universe, everything from the atoms that you and I are made of, crazy particles called neutrinos, mysterious stuff we still don't know what it is, this dark matter. And I won't talk about that tonight, the detector, but if anyone wants in the Q&A at the end to bring it up, that's a hint, please do, that would be amazing. But I am not a particle physicist, which means, disclaimer, I will try my best to answer any of your questions in the Q&A, but I reserve the right to throw to an expert, and I know he's around, so we'll just tweet that question to Professor Brian Cox, and hopefully he'll get back to us. So I thought I'd kick off this evening by showing you our universe. It's a wonderful app. A friend of mine, a colleague, Danela Breshko from the University of Western Australia, created this. It's called Cosmic Eye. Don't download it yet because you'll crash the Wi-Fi. But after, please remember to download this. It takes us on a journey through, essentially from the scale of you and I, meter scale or so, all the way up to the very largest scales of the universe. And as we'll see, all the way to very much smaller scales. So we start off, we zoom in into Louise, as it turns out, Louise's eye. We see the retina. We go into the blood vessels, and we're going to go into a white blood cell. We keep zooming into smaller scales, and now we see the chromosomes. We zoom in to those, and we see these strands of DNA tangled up. We go deeper into this, and we see the clouds of the electron around an atom, and then nothing. And we have to keep zooming in and zooming in, zooming in, until we see the nucleus, the center of the atom made up of protons and neutrons, each of which contain 3 quarks. So that was the zoom in. Get his app and you get the bigger picture. The scale is hard to comprehend. So in that zoom in, it was essentially a powers of 10. We were zooming in. But an analogy I'd like to use is, this went wrong yesterday, and Isabel saw this, and this was embarrassing. Let me see if I can just get one hair this time. Oh no, I'd got a whole bunch of my hairs again. I'm going bald with this talk. So, here we go. My hair, 2 strands, as it turns out. It's about 100 microns thick. It would be thicker, but I use really cheap shampoo. If I were to take this hair and expand it to the size of the powerhouse, then in that giant volume, an atom would take up no more space than this hair. The entire volume of the powerhouse and individual atoms fit inside this hair. And that's old hat. Atoms are easy. Now we zoom in to the atom. So we take the atom, we increase it to the scale of me, of my body, and then we ask, well, what size is the nucleus, the core of the atom? And it's the thickness of this hair, which means all of the rest is empty. The atom is vastly emptier than the solar system in terms of scale. If you go out to Neptune, the furthest planet, and yes, I'm aware that's controversial, from the sun, and you think of all of that emptiness of space in the solar system, and how packed and concentrated most of that mass actually is in the center of the sun, that's actually 1,000 times more spread out than how densely packed the atom is, with all of the mass in the nucleus, which is now no bigger than this hair, while the rest of the atom is the size of me and completely empty. And then we zoom in. And now we zoom in to the nucleus. And we expand the nucleus, the core of the atom, to about the size of this stage. By this point, an individual proton, one of the particles that make up the nucleus of the atom, the other very common particle is the neutron, that's about the size of my head. Do you want to get some water? Seriously, if you want some water, we actually have. So we have our proton about the size of my head, and the smallest scale that the Large Hadron Collider has probed down to is this hair. At this stage, on the scale that the smallest features the Large Hadron Collider has explored, the atom that we started to zoom into is now 10 kilometers across. And my initial hair that started this all, on that scale, now stretches 20 times further than the moon. The Large Hadron Collider is a microscope. It is the most staggeringly complex and powerful microscope in history. But let's take it back. It's one thing to talk about a microscope, such as the Large Hadron Collider, but for some of us, myself included by the way, maybe haven't used a microscope recently, let's get back to basics. So we have this beautiful microscope from Robert Hooke in the 1600s. This is an optical microscope, visible light. With that, Hooke was able to see the details of an ant and the details of a flea. Previously, just an impossibly small, boring-looking creature, now revealed to have all of this fascinating structure. And he published this work in Micrographia. Now, with an optical microscope, you can only see down to the level, to the scale of what we call the wavelength of the light. Light is a wave, sometimes. Peak, trough, peak, trough, peak, trough. The distance between the peaks is the wavelength. If what you're looking for is smaller than the distance between those peaks, essentially the wave just goes around it. Doesn't interact, doesn't bounce off it. In other words, you don't see it. Because to use a microscope, you're relying on light bouncing off the object of interest and coming up through the eyepiece. And if what you want to look at is smaller than the wavelength of that light, it just won't be possible to see it. Now, light has a very short wavelength. Green light is, roughly speaking, about 600 nanometers. That is 0.00000. How many O's did I just say? 06? You can see it. To use scientific, the numbers are about to get ridiculous, by the way, so we're going to have to switch to scientific notation. So that is 600 times 10 to the minus 9 meters. That's a nanometer, so 600 nanometers. So that's basically, if we scratch out those two zeros, that would then become minus 7. But I kept it as minus 9 because it's a nanometer. So one way to think of light is having this wavelength. Another way to talk about light is the energy of that light. And you can measure the energy of the light very simply. It is inversely proportional to the wavelength. In other words, the shorter the wavelength, the distance between these peaks, the higher energy the light is. You're packing more waves into this narrow bunch. Essentially, you're concentrating the waves and having a higher energy. Now, green light is about, as I said, 600 nanometers. Blue light is 500 nanometers. The distance between the peaks is less, so the energy is more. Blue light is more energetic than green light, and ultraviolet, which is an even shorter wavelength than blue light, is more energetic again, and you will certainly have felt this if you've gone to the beach and not slip, slop, slapped. Is that the expression, by the way? I always get this one, slip, slop, slap? Yeah, excellent. All right, just checking. We could have tweeted that to Brian Cox. I don't think he would have got that answer right, by the way. So in this example, lambda the wavelength is 600 nanometers. What energy does this correspond to? The formula, I'm sorry, there's a couple of formula. Vast majority of you, please ignore it. For those who really are, want to know about these things, I've put this in, but I hope everyone is going to enjoy this talk. But this is, I feel naked without putting a formula on, I'm sorry. The energy of that light is calculated by taking what we call Planck's constant, a tiny number, multiplying it by the speed of light, which is a very large number. The speed of light is very large indeed, and then dividing it by that wavelength. And we get an answer of 2 eV. And eV is the currency of particle physics. It's an electron volt. It's the energy of an electron that is accelerated through 1 volt. I didn't say it was a particularly good unit, by the way. It's the common one we use in particle physics. An electron volt is a tiny number. 1 trillion electron volts has the energy of a mosquito flying. And yet you can use such weak energy to see the world around you because your eyes are fantastically sensitive instruments indeed. So the idea is, with optical light, if you want to see finer detail, you have to use shorter wavelengths, higher energies. But then, how do you zoom in? Who knows what this is, by the way? Shut up, yep.
Well, cells and bacteria and viruses and whatever we like to
Yeah, it's certainly, it's almost on that scale. It's actually less, well, I was about to say it's more innocuous than bacteria. No, who's it? Pollen? Pollen, yes. This is pollen. This is the stuff. I was about to say it's more innocuous than bacteria, but I hate this stuff. This stuff makes my life a misery in the summer. This is pollen, that invisible stuff that gets up your nose and ruins your summer. This is what different types of pollen grains look like. They are far smaller than light can see. An optical microscope would not reveal this detail. So how did we see it? Well, we could have used ever shorter wavelength of light and gone all the way up to X-rays. Tends to destroy things, though. Instead, we bounced not light rays off it, but electrons. We actually tapped little electrons onto these and received the reflected electrons back. Because matter actually, just like light, can be a particle, but can also be a wave. There is a wavelength associated with matter, with atoms, with electrons. It's very short, which is why you tend to see, you don't see things like, my clicker just like rippling away, like a wave. But on tiny scales, the matter will have a wavelength. We call it the de Broglie wavelength. And everything I've just described about being able to see finer details by using shorter wavelengths of light holds true for particles as well. And because their wavelength is so tiny, because they kind of do look like point particles after all, we can actually resolve these kind of details of the tiny world that we live in. Now, this is the formula for the de Broglie wavelength. Again, h, the Planck constant divided by p, which is the momentum of that particle. I'm sorry, this equation's about to get bad. Sorry. You can calculate the momentum of a particle, or indeed of light as well. You work out basically its total energy, which is its energy of motion, and what we call its rest mass energy. And we'll get to the idea of E equals mc squared. I think a number of you may have heard of this before. This simplifies the equation a little bit, just separating out that idea of the kinetic energy. Because you have a particle's mass here. So even relatively slowly moving electrons with a very low kinetic energy, the energy of motion, that idea is important. I'll just reiterate that. The energy you get from moving. But even if you're moving slowly, your electron has a mass and has an energy of that as a result, and that is far greater than light. It's about 250,000 times more energy just by the virtue of existing. And remember, the higher the energy, the finer detail you can see. So suddenly, by using electrons, even if they're hardly moving at all, you have the potential to be 250,000 times magnification, or zoom in on these objects. So this is why particle physicists began to hit stuff with particles to see it better. Now, for this particular case, we're firing the electrons with an energy of about 2,000 electron volts, this idea of keV. We're not worried too much about these numbers, just to point out that gets you to this kind of scale, which is, well, I didn't mean to do that, which allows you to resolve these kind of features. Again, this is the scientific notation. This is 0.0, hang on, I'm going to use my hand, 0.00000000001 worth of a meter. Pretty small. But that's the kind of resolving power you have when you use electrons. Okay, so here is the idea of the atom. As I mentioned, this incredibly small, pretty much empty object, horribly out of scale. Remember the idea, to get to the smallest scales of the Large Hadron Collider that is probed is basically the scale of these quarks. This atom would be 10 kilometers across if these quarks were drawn as a hair width. So a little out of scale, but instructive nonetheless, because what you see here are the typical sizes of the different components of the atom. And we know from the horrible equation I just showed, to be able to get to that kind of scale, the wavelength of the particle, the de Broglie wavelength, you can increase the energy. So there's that horrific equation again. With 200 million electron volts, we're really ramping up that electrical generator and really pumping a massive voltage across to fire up these electrons. We can get to a scale of about the nucleus, 10 to the minus 14 meters. I'm not going to do that number of zeros. A lot of zeros. We go up to 2 billion electron volts, and we probe a scale of 10 to the minus 15, which is essentially the individual components, the protons and the neutrons of the nucleus of the atom. 2 tera electron volts, again, 2 trillion electron volts, we'll get up to 10 to the minus 18. This is basically getting interesting. And then when you hit 7 tera electron volts, you get to 10 to the minus 19. In other words, you get to understand, begin to probe what's inside the protons and the neutrons. Now, this is the number the Large Hadron Collider operates at. There's actually a reason, a particularly special reason for that. So you've seen the collider exhibit. What is a Large Hadron Collider? Well, it's a giant ring in which you accelerate these particles around in these giant tunnels, superconducting magnets, taking up to incredible energies, smashing them together, and getting all these fragments out. Doesn't look like much of a microscope to me. Now remember, the idea was to hit small things ever harder to see more detail. One way to guarantee you get it really hard hit is to have two things crash together. And to a certain degree, you'll be able to do that without destroying the thing you're looking at of interest. But fundamentally, if you keep getting the energies high enough, you're going to slam them together and anything is going to disintegrate. And at that point, you're no longer looking at these small scales in a traditional way. Instead, your picture, your window into this is something called the standard model of particle physics. It is the actual stuff that comes out of the explosion. It tells you what it looks like on those small scales. And that's because of the idea of Einstein that E equals mc squared. This idea is super bizarre, by the way. And I want to remind you of c, the speed of light, big number. Light travels really fast. M is mass, and E is energy. A little bit of mass times the speed of light squared, so you're taking a big number, you're squaring, which is insane, means you get a lot of energy out. That hair that I showed earlier, if you converted that mass entirely to energy, that would vaporize Sydney. It's 4 times greater energy than the bomb that destroyed Hiroshima. There is a lot of energy locked up in mass, which is why nuclear bombs are so scary. It works the other way around too, though. If you have it takes a lot of energy to go the other way, to create mass, but you can transfer from one to the other. If you slam enough energy together, you can make a new bit of mass. And if you take 2 light particles and ramp up their energy, which is the energy of their motion, enough, and you slam them together, you can create new, heavier particles, more massive particles from that collision energy. This is fundamentally ridiculous. Because I have a car. I travel at great speed. Again, my kinetic energy is vast. I have another car. And I collide those cars, and there's a massive burst of energy. And out pops a ship. Two lower mass objects colliding together with tremendous energy created a new, heavier object. It doesn't happen on the scale that we live in, and yet it happens all the time on the scale that atoms live. And this is happening in the Large Hadron Collider. Huge energies are collided together, and new particles are created. And the exact numbers and ratios and what comes out of those particles, that tells you what that universe looks like on those smaller scales. It tells you about the physics at play. The problem with being a heavy particle, by the way, a big object, is that you tend to fall apart. The ship would just explode mere nanoseconds after it was formed. And a shower of debris of other types of lighter particles would cascade out. And from that fragment, from all of those pieces, your detectors at the Large Hadron Collider capture them all, and like a giant CSI ballistics kind of episode, try to put it all back together to understand where the explosion came from, what particle disintegrated, what did the universe look like on those small scales at the point that you hit it so hard with such high energies, you could see those smallest scales. Now, this sounds all well and good, but seeing is believing. Can you see these subatomic particles? Now, I've just spent literally 20 minutes telling you that you need a Large Hadron Collider to smash these things together, tremendous energies to do so. But there's an easier way, and that is a Clyde chamber. This is an example from Carl D. Anderson. Basically, we have a box with a vapor, and as a particle smashes through that gas, it seeds a Clyde behind it. And here we see a positron, the anti-particle to the electron. This is the first time we ever saw one. It's bending because we have a magnetic field across this box. An electron would bend this way. The positron has the opposite charge, so it bends the other way. So you can see the tracks, and you can actually begin to map out and understand what it is you're seeing. Now, that was a while ago. CERN has done a little better. Here we have a particle come smashing in. It fragments and unleashes a cascade of new particles. You are seeing E equals mc squared in action. All of these particles, we have the ones that are turning in big arcs. They have greater mass than the ones that spiral inwards. In other words, the ones that do the little spirals are the electrons, and the protons are the ones that spiral more slowly or more lazily because they have greater mass. And then there's just a whole lot of other stuff. I mean, there's crazy stuff going on in there. So with these maps, you can actually create a snapshot. You can see the subatomic world made real. By the way, this technology is called a bubble chamber. They no longer use it at CERN. I'm tremendously upset about this because they have digital cameras. That's what the Large Hadron Collider is. Basically, instead of taking a picture and having, grad students look at this, you just capture it in a digital camera, a giant CCD, which is what the detectors are. Now, I want to give a plug. In the powerhouse, there is a Clyde chamber, which isn't working tonight, I've just been told, so I'm so sorry for building it up a little, but it will be soon. And Mark sent me this video of this Clyde chamber. It's a little bit faint, it's not as fancy as CERN's, but you can see those particles shooting through. These are subatomic particles. See, there you go. That straight line, high energy, didn't deviate. It's probably a proton. There's no magnetic field, so they'll just continue straight lines. There's another really clean. These are cosmic rays from space. Where is the next one? Where's the next one? Where's the next one? Went quiet. Oh, God, I missed one. There was one right there. Oh, no. I'm sorry, I'm getting really fascinated. Oh, that little one. Okay, so that was a little short track, which means it was an ionizing particle, probably an alpha particle, probably the nucleus of a helium atom. I feel like I'm missing several others. It's one of these things you just catch it out of the corner of your eye. Oh, yeah, there's none. Okay, so what you're seeing are actual particles. Some of these particles are from space. They're crashing down. Some of them are natural radiation from the background. You can just, honestly, and I have, spend hours looking at these things. They're really easy to make. I'm saying on behalf of Mark. I've never tried to build one. In principle, I've looked it up, and I think it's actually quite easy to do. But don't hold me to that. But I do encourage you. It's totally safe. It's totally, in no way poisonous. Please do try to create this. And then freak yourself out as you watch radiation from space ripping through this Clyde chamber and imagine what that's doing to your body. So, we've moved on. The Large Hadron Collider in Geneva, a 27-kilometer ring in circumference under the city with 4 detector sites. CMS and ATLAS are 2 general-purpose particle finding machines. They're looking for the new particles. ALICE slams together not protons, but lead nuclei. So you strip the electrons from the lead atoms, and you fire them together. And this is why we call it the Large Hadron Collider, not the Large Proton Collider. because of this experiment, essentially. And it's trying to recreate a new phase of matter. We have solid, liquid, gas, plasma, arguably, where you strip the electrons from the atoms. And then, when you slam lead nuclei, the protons and neutron bundles together hard enough, they actually melt, and you get a quark gluon plasma, or soup is the nicer term. We think we may have actually just begun to see that new phase of matter in this last collision. And then there's the Large Hadron Collider B. B is for beauty, which is the nicer term for what is called the bottom quark. And this has a very important role to play, and I'll hopefully get to that before the end of the talk. The experiment works by firing bundles of protons around the ring, but it all starts off somewhere. In a little canister of hydrogen, we strip the electrons off those hydrogen atoms, exposing the proton. Now bare, it's charged, and we can send it through this linear accelerator. This is a drag race. We start here, and we just burn rubber from one end to the other. Magnetic fields are grabbing, and electromagnetic fields are grabbing this naked charged proton and firing it up. By the time it leaves the end of that straight accelerator, it's at a third of the speed of light. The problem is, like a drag race, you just run out of road. We would have to keep building these things ever longer to get to higher energies. Or, if you're clever, and CERN is nothing if not clever, you make them do doughies. So now we fire into a ring, and they make laps, again, boosting ever higher. These magnets are grabbing them, bending them around the track, increasing the energies ever further. You run out of track, you go to the next bigger one. By this point, we're at 99.9% the speed of light. We keep going, building up ever higher energies. We then go onto the super proton synchrotron. Again, bigger ramp, higher energies. This is now at half a tera electron volt energy scales. Previous generation collider, basically. And then we get into the LHC, 27-kilometer ring, tremendous speeds, and we get a head-on collision. Now, there are, by the point of the collision, the particles are traveling at 99.9999991% the speed of light. They each have 7 tera electron volts of energy, so when they collide, we're going to be probing the scales, those smaller scales where the quarks begin to live. When you do this collision, you're doing all this to zoom in. You're doing all this to basically be the most powerful microscope in the world. That 27-kilometer track is lined with these superconducting magnets. They create a magnetic field so intense it can actually hold on to those insanely moving particles that have just made over 11,000 laps each and every second. That magnetic field itself is about 100,000 times greater than the entire Earth. And you do all that, so you get a collision that when it occurs at this ridiculous energy, basically equates to 100,000 times the temperature of the core of the sun, which is a wonderful fact and completely meaningless because I can't even comprehend how hot my meal is. I frequently burn myself when I eat. I don't even understand how hot that can possibly be. Another way to think of it is it's exploring a time in the universe's history about 1/1000th of a second after the Big Bang. It's recreating conditions that haven't been seen for most of the universe's history. Now, in doing this experiment, you're powering those magnets with about enough electricity to power 500,000 homes. which is one reason the Large Hadron Collider stops at Christmas, by the way, for the winter, because you can't buy the electricity. Geneva needs it. They need their heating. Not actually kidding. They had to turn it off. All of that is to ensure that particles slam together these incredible speeds, incredible energies, to zoom in to see the smaller scales, recreating a condition 100,000 times hotter than the core of the sun in a detector that's kept colder than space. And the reason it is so the magnets remain what we call superconducting. In other words, they can carry that much electricity without resistance. And as soon as they heat up, then they have resistance. And suddenly, 500,000 homes worth of electricity gets dumped into the magnets, and they melt and explode. And it's horrible. And it kind of did happen already. So it sort of set the Large Hadron Collider back a couple of years. So this is an unbelievable engineering program. Oh my goodness, I've just seen the time. Excellent. So let's quickly on. We have a smorgasbord of new particles. This is our bubble chamber. We're seeing all of these incredible new particles and fragments coming from our exploding battleship. These are captured by the detector that sits around it, allowing you to recreate, understand what the particle was that gave birth to all of these fragments. Now, this is the ingredients list. I really am not going to go through this now at all, but basically here are the quarks, here are the electrons. Forms a sort of a nice diagram. There's, for some reason, 3 sets of ever more massive fragments or subatomic particles, but these are the only ones you need to worry about. Up quark, down quark, and an electron. 2 up quarks and a down quark make a proton. 2 down and 1 up quarks make a neutron. Those things together make your nucleus, and around it circles the electron. That's it. Everything else is just a particle waiting to fragment and explode and decay into one of those. However, there is a little guy. It's not a little guy, it's an absolutely enormous particle. It's called the Higgs boson. I think you may have heard of it, AKA the God particle. This was a just frankly insane idea proposed by Peter Higgs. Here he is sitting in front of CMS, the detector, one of the detectors that would ultimately find his particle, and he's looking a bit grim because they hadn't found it at that point. This is before. So maybe he rubbed it for luck, because it was just after 2 years of searching, they finally confirmed this particle existed. The Higgs boson gives mass. Well, I should say, sorry, the Higgs boson is a particle that is formed when you smash the Higgs field really hard. The Higgs field is a basically really good Wi-Fi coverage through the universe. It extends everywhere through space. And that field, again, just think of a Wi-Fi signal permeating out. That field gives particles that we are made of mass. How does it do that? Can I have 6 volunteers to come on the stage, please? Yes, you 2, up. And, oh, well, and mum, yep. And behind, yep. Okay, that's 3, come on. It's going quick. 3 more, yes, sir. And 1 more, 2 more, I can't even count anymore. Right at the back, right at the back. Yes, the young man standing up, thank you very much. Yep, excellent. All right, and white shirt. And that will do, thank you very much. All right, round of applause for our volunteers. Okay, so we are, my goodness, that was amazing. You're just like ordering, yeah, come on stage, please come up. Oh, it's okay, come on, it'll be fine. Because we're at a party.
Which one do you mean? Because
It's totally fine, more the merrier, because this is a cocktail party. That's what we're doing here. And like any party, you stand in a straight line and look in one direction. So, spread out a little bit. you know, just through the stage, mingle around, just amuse yourself. Take it easy, it's a party. It's not a great party, just saying, it's just a party. Good point though. Okay, so in the setup of the Higgs field, the beautiful explanation of how the Higgs gives mass is the party analogy. In this party, you are all the Higgs. You represent the Higgs field, okay? You're all floating around, you're having fun. I'm a particle, and I come in through one side, I'll come in through this side of the room, and at this party, you just don't care about me. I am not very popular, and that means when I walk into this party, I'll be able to basically walk straight through you, and none of you are even going to bother with me at all, and my heart is breaking, and no one stopped to chat, and that's it. I just walked across the room. A particle that can move quickly from one point to another is easier to move, is a lighter particle. Yes? Think of something that's light. Is it easier to move than something that's heavy? All right, we'll reset this. And now I'm someone fantastically popular that you all want to meet. I'm Professor Brian Cox. So now when I arrive at this party, and oh my goodness, I'm trying to get over this way. Oh look, oh no, I've got lots of fame and I can't, everyone wants to talk to me. And I just get nowhere. And in being unable to travel very far, very quickly, it's kind of like I have a lot of mass. And the Higgs field, by interacting more strongly with certain particles rather than others, gives those particles the property of greater mass. And that is the cocktail party analogy. Could you thank the fantastic volunteers again? Thank you so much. That was awful being Brian Cox there for me. I always thought it'd be cool, but too much fame. But it was beautiful. So, that was my Brian Cox impression. All right, so we created the Higgs boson, confirming the Higgs field's existence, the thing that gives mass to everything. We could also potentially create something else with the Large Hadron Collider, and that is black holes. Scary, right? All-devouring objects that lie in space and bend light around them and swallow stars. Unfortunately, not these kind of black holes. The Large Hadron Collider might create microscopic black holes on the scale smaller than the nucleus of the atom. In that black hole, thanks to something called Hawking radiation, Stephen Hawking told us those little black holes would just evaporate. They would explode. Very characteristic signal. If we saw that explosion, we would know instantly that one, black holes could be created in the Large Hadron Collider. Two, that Stephen Hawking is yet more of a genius than we already thought he was. And three, that he now gets a Nobel Prize. Sadly for Peter Higgs did get the Nobel Prize. Sadly for Stephen Hawking, we haven't. But that didn't stop some fabulously responsible reporting by some British newspapers. So, why didn't the Large Hadron Collider destroy the Earth? Was because we didn't create any black holes. But how could we know that that was going to be safe even if we did? Because Hawking could have been wrong. The reason is because nature has undertaken 1 million Large Hadron Collider experiments in the last billion years or so. And that's because of radiation from space, these cosmic rays. You saw some of the tracks in the cloud chamber, the particularly straight ones, slamming in with huge energies. They hit the Earth's atmosphere at energies far in excess of anything the Large Hadron Collider could create. And they, if they do form black holes in that collision, they certainly then don't lead to Earth's destruction. And the definitive proof for that is undoubtedly, ta-da, that we're here. So we know that that's not going to be possible, and even if the Large Hadron Collider was to create the black holes, that they would still be safe. But it made for good copy, so, you know. All right, as I mentioned, we have basically the Large Hadron Collider is a time machine probing back to the earliest moments of the universe. This is the final equation I want to show you, which is the standard model of particle physics. It is the picture of the universe on those smallest scales. You plug in what the particles slamming together, what you're trying to look at, the energy of those particles at the smallest scales, and you get out what that universe looks like, which is, you know, a fiery mess of death as these particles collide. This is obviously the cute cuddly version. This is if you expand it out. I lied. That wasn't the final equation. This is the final equation. No one said science was easy. Physics is hard, but it's also awesome and absolutely worth learning how to solve these kinds of equations, because you get to work at CERN. So, what can we hope to do with the Large Hadron Collider? Well, one of the challenges we have in physics is that this beautiful model of the standard model that explains everything that we're seeing from the Large Hadron Collider doesn't play nice with the other fantastic model we have in the universe, which is Einstein's theory of general relativity. They just don't work well together. What we hope to do is have some genius, potentially one of the volunteers I got up earlier who are now inspired to get into physics, because then they get to go to cool parties as well that don't have any bars. Seriously, that was funny. That was a great line. We hope that person may create the theory of everything, unifying all the laws of nature. We also have a bit of a mystery. It's called E = mc squared. We started with this, we're familiar with it. I didn't tell you everything about it. And that is that when you get energy, you create mass, you create a particle, and you create its antiparticle. You create an electron and a positron. You always create these things in pairs. The problem with that is, when they meet, they annihilate. If, after the Big Bang, you have all this energy, and it's turning into matter, which is what we have, every particle you create is coming with its evil twin, the antiparticle, and they'll annihilate in a flash of light. For some reason, 1 pair in a billion don't. And everything we see is from that imperfect calculation. So when someone tells you you're 1 in a million, they insulted you. You're 1 in a billion. We don't know why. So we don't know why about you not being 1 in a million. You're great, you're great. We don't know why this asymmetry exists. And that's what the LHCb is trying to find. We think the bottom quark might be responsible, but we don't know why yet. So that's one of the big mysteries. The other is dark matter. This is what I work on. This is my thing. I'm really upset that I can't talk about it for any longer. It is a new type of particle that exists in the universe that holds the galaxy itself together, because we can map out the motion of the stars and the gas, and they reveal the presence of an invisible companion pulling at them with its gravity, much as, although the air is invisible, we can see the motion of the trees through the wind, and we can assess that it is indeed there. And doing that, we can weigh it, and we come to the astounding conclusion that 5% of the universe is everything we can see, all of those galaxies and stars. 5 times more, this is embarrassing, 5 times more is dark matter. And this is a map we made through the bending of light by the dark matter. So we vaguely know where it is. We know exactly how much it is. This invisible stuff outweighs everything you can see 5 times over. But we don't know what it is. But we could create it at the Large Hadron Collider through one of these collisions. And what we would see is the energy going in, which we know. We capture all the fragments that come off it, and we add that up. And we see that there's something missing, because the dark matter was created and, like a ghost, flew straight through the detector without ever triggering it. Accountancy can be cool. but only if you're doing it for science. The other fraction, by the way, I hope some of the accountants in the room did note my terrible pie chart. It is missing a little bit. Of course, this is 69%. 2/3 of the entire universe is made up of dark energy, which we don't know. We don't know what it is. In honor of the experiment, the center CERN that gave birth to the World Wide Web, I gave dark energy, of course, the 404 number. Any tech geeks in the audience? I'm assuming that was you laughing. So, the Large Hadron Collider, potentially answer the question of why is there anything here at all. It can zoom in on that embarrassing large fraction of the universe that we know is out there but can't see, the dark matter. And maybe it can give us a hint as to a potential theory of everything. And I want to remind you all that the Large Hadron Collider, fabulous as it is just a staggeringly expensive bit of machinery without the people to run it. That includes scientists and engineers, thousands of whom spend their lives working in this phenomenal research environment, uncovering those mysteries. And I hope, for some of you at least, you're inspired to take up that opportunity in the future and become a scientist or engineer. And with that, I would wish you a smashingly good Sydney Science Festival.
We have some time to take some questions. So who has a question for
Do we have time?
Yeah, we have time.
I thought I didn't have time. I want to hurry.
No, you're all right. Yes.
Thanks for the great talk.
Pleasure.
You mentioned in the detectors, it showed in the image that it looks like a cloud chamber, basically.
Yeah.
I thought it was a vacuum, but if it's not a vacuum, if there is actually a cloud chamber in there, how come the particles collide with each other and not with whatever the cloud is made of?
Yep. Great question. So the tunnels are indeed vacuums, as you're correctly identified. They have these little bunches of 115 billion protons, little packets of them, and they're colliding. There's 40 million of those collisions every second. So it's a vacuum, but there's still a lot of interesting little objects in there. The cloud chamber was how we used to do it. Now, thanks to the detector technology, and I really do mean just silicon chips, right? Just actual digital camera style technologies. The collisions, when they occur in this vacuum, they fly out and they fly through that detector, through the actual camera itself, striking through the electronics and are recorded, and their trajectories are recorded as they go through the detectors. So the ring is a vacuum, absolutely. The particles meet at 4 locations around which we've built this detector to capture all of the fragments that come from that explosion. So those trajectories and tracks look like the old cloud chamber experiments, but the way we're actually tracking them, we're not relying on the gas to be ionized, or to be, in the case of the gas chamber, to actually be supersaturated and form a cloud. We're just using the actual electronics themselves, which is great, but I kind of like that old school and analog style, says the man who has MP3s and not actually vinyl. But yes.
With dark matter, as it doesn't emit any electromagnetic radiation, is there any other way to detect it other than the effects of its gravity or the absence of particles?
Excellent question. Yes, so dark matter is invisible. It doesn't absorb or emit light. It has gravity. But we hope it also does interact by essentially having a head-on collision with the nucleus of an atom. Now, most of the atom, as I said, is empty space. And if you think about the chances that you're just flying through the solar system, which is, big and empty, and you're just minding your own business, you're flying through, and you just wallop the sun, right? Like head-on into the sun. That would be pretty unlucky. Just look at the sky the next time. Look at how big the sun is on that sky. Don't look directly at the sun. In fact, if you put your thumb up, okay, the moon is the same size as the sun, by the way, on the sky. Weird coincidence. And it's safer. So do put your thumb up to the moon next time, and you'll see it will just be with your arm stretched out, and it will just be about the size of your thumbnail or so. It's about half a degree on the sky. The rest of the sky is empty. So the chances that you hit that sun is remote. And yet that is 1,000 times more spread out than the nucleus of the atom. So the chances of a dark matter particle just doing its thing, just moseying through, slamming into the nucleus, incredibly remote, which is why it's been so elusive for so long. But we're building a detector in the bottom of a gold mine in Stawell, Victoria. This detector is called SABRE. And with this detector, it's basically a very special crystal that will flash if a dark matter particle hits it. Hits the center of the atom, one of the crystal. This will emit this little flash of light. The problem is it will also emit a flash of light if anything hits it, like the radiation from space, and we could see that in the bubble chamber, and that was happening, well, in those 20 seconds, there was at least 8 collisions. So that would completely blind us to the radiation, to the dark matter. So we take it a kilometer underground, and we use that kilometer's worth of rock above to block all the radiation from space, but this ghost-like dark matter just makes it straight through, unimpeded, and very occasionally there, in the dark, in the bottom of a gold mine, we're looking for a crystal to flash, revealing the fact it was struck by a ghost. Cool project to join. It will still be there when you go to university. Please look us up.
If you got a mole amount of particles and put them into a box,
Yeah.
roughly how big would the box actually be?
Okay, so a mole is a measure, or a standard measure of a number of atoms, which is basically Avogadro's number. Well, that is. Whatever that's 6 times 10 to the 24? 23. 23? Damn, I always get that one wrong. So let's think about that. So that would be about a gram per mole for hydrogen, or a kilo. In any case, depends if it's in a gas. So the extent of, well, yeah. So much more important is what state is that in. If it's a gas, then at room temperature, a mole of gas will be about 1,000 liters, I'm guessing? Just off the top of my head, if anyone knows the answer to that, some chemist in the room? 24.4 liters, perfect. So that was the answer. You can tell I don't do chemistry, by the way. We don't use moles in physics much. I mean, you do when you're learning it, but then when you do it for research, you don't. We use horrible units like electron volts. We use horrible units like the, oh God, even worse units called natural units, where you set the speed of light to 1 and big G to 1, and then you set some other thing. And then you wonder why no one gets the answer right in quizzes, because you basically are screwing up the units. So yeah, so I haven't used a mole for basically 10 years. I think that showed, so thank you. Was there another question? Oh yeah, well just, yeah.
If you had the same money, time, and number of personnel that CERN had for dark matter,
Yeah.
would you still do SABRE, or would you do something different?
If I had the resources of CERN, so I'd go to Vegas. I would still do CERN. I would still do SABRE, because the two ways you can explore dark matter, you can either try to create it in the collider, or you can wait for it to come to you. And dark matter is always doing that. So it's always flying through us. So at one level, you can build a bigger SABRE, which we already have plans to do, where you have it running for a few years, and then you have a bit more money, and if I had all the money of CERN, then I would do that now. I would build an extra supermassive SABRE, and just have more crystals around it, increasing the chances that the dark matter would collide with it and giving this flash of light. The problem with that approach is that you get to, ultimately, you reach what's called the neutrino background, and that's because the sun is a giant nuclear furnace undergoing fusion where hydrogen is combined to form helium, in the process emitting tremendous amounts of energy overall. 1 million tons per second of hydrogen is being turned into helium, and E equals mc squared. Helium weighs less than the 2 hydrogen atoms combined, which means a little bit of mass has been transferred into a lot of energy, which is why the sun glows. Also through that is a neutrino, anti-neutrino, but whatever. Those things flood out of this giant reactor in the sky, and they are, again, ghost-like particles. The problem is if you build, in the next 10 years, even without CERN's funding, our detectors around the world will get, our dark matter detectors will keep getting bigger, and in 10 years they will be big enough that they will now see the neutrinos from the sun. And you can't escape those. They fly through anything. A kilometer's worth of rock will shield you from radiation from space, mostly. To shield yourself from the neutrinos, you have to get a bit of lead, roughly speaking. This is the sun, and this is the nearest star. Even with CERN's budget, I can't afford that much lead. So to block the neutrinos would just be impossible. There's ways you can get around it a little, but fundamentally, if we don't detect dark matter in the next 10 years in our detectors underground, probably the only other chance will be either directional detection or ramping up CERN to an even higher energy to hopefully create the dark matter if it hasn't already done so. So CERN might come asking us, the rest of the community, for money to do that. Was there any more questions? Yep.
This is the last question.
You mentioned that you can take light and ramp the energy of it up and bombard it together.
The light?
Yes, you mentioned that earlier.
Yeah, yeah.
How do you do that, and what does it produce?
Okay, so you can, so all of the collisions are involving particles. Their actual rest mass energy is enormous. But yes, you can accelerate, you can use higher energy light. So examples are ultraviolet, and then we would get up to X-rays. So routinely, for anyone who's had a dental X-ray, yay, you go, well, no, boo, it was probably for a bad reason, sorry. But I meant yay because you've experienced a very high energy form of light that's probing you on a tiny scale. The higher energies than that, you can ramp up and you can create that, in the case of X-rays, you can old school TVs, the cathode ray, where you would have a, you would basically accelerate up electrons, and as they break, they slam into the end of that little tube at the back of your TV. They would break and they would throw a huge amount of X-rays out, and that's actually what would then illuminate, the electrons would be illuminating or causing phosphorescence of the TV, which is what you're then seeing as the picture. But you've got all these X-rays blasting out, so you don't die from that. They put lead glass in the front of your TV, which is why it's so heavy. If anyone's ever tried an old school TV to lift it. It's obviously all plasma and digital ion, you know. Kids don't know, they're born. But for anyone who's tried to move unis with one of these TVs, it's backbreaking. And it's because it's lead lined, essentially. Even higher is gamma rays, and something spectacular happens when you get to gamma rays. With high enough energy light, it will spontaneously become a particle. And your light will actually convert into usually a positron and the electrons. The electron goes around the atoms and its antiparticle pair. And we see anti-electrons, these positrons, all through space. Not in vast quantities, but certainly some. And in fact, there's a detector on board the International Space Station called AMS, and it's actually tracking some of these positrons. So you can certainly, by ramping up the energy of the light enough, you can get your, you can create new particles, but it's just a very inefficient way to get to those higher energies. It's way easier to start with an existing particle and ramp that up, because you already start, you know, with 250,000 times more energy in just the mass itself than going the old route of the light. But definitely, those kind of accelerators, the main one is a fabulous instrument in Melbourne, called the synchrotron. It's a light beam source, so you can do spectacular science with it, just different to particle physics. But you can examine material science, you can explore the makeup of crystals, of protein structures, you can use it for all of those things. That's a good question. All right, is that it?
I just had a thought. Looking at this is so beautiful. I think this is potentially really like as brilliant as the Large Hadron Collider. If you printed that, wouldn't it make an amazing bow tie?
Oh, well, that's happening. That's amazing. Awesome.
Thank you so much, Alan, for being here with us tonight. Give him a round of applause.
Thank you.
This is just the beginning of Sydney Science Festival, so make sure you go to the website, sydneyscience.com.au. There's heaps of events all over the city. Have a wonderful night, and we'll see you soon.